have started into previous classes. Today we want to talk about converting integral equation to ordinary differential equations and vice versa. I mean ODE to integral equation and integral equation to ODE. It means that when an integral equation is given to you, how you can transform it to an ordinary differential equation and sorry, we have two of your classmates in my office, and because of this reason, I muted my microphone. Okay, let's continue. I was talking about how to convert a given integral equation to an ordinary differential equation. In another hand, if an ordinary differential equation is given to you, how you can convert it to an integral equation. Before starting the discussion, we first should learn how to take derivative from integrals. We need very important formula, which is known as Leibniz rule. Using this formula, we will learn how we can take derivative from an integral. For example, to differentiate the integral of g of xt with respect to the variable t from alpha of x to beta of x with respect to x. So here, let me mark it here. The outcome of this integral is a function of the variable x. So we have a function of x. We can denote it by the function f, and this function is in terms of the variable x. So we have a function of x which is given by a formula of integration, and we want to take derivative of this formula. For taking derivative, we apply the useful Leibniz rule. What's the Leibniz rule is? Let's check here. The derivative of this function with respect to the variable x is equal to g of x and beta x times derivative of beta with respect to x, or beta prime of x, minus g of x alpha of x times the derivative of alpha with respect to x, or alpha prime of x. Here we have the upper bound instead of t. Here we have the lower bound instead of t. And the final part is the integral of partial derivative of g with respect to x in direction t from alpha of x to beta of x. So if an integral is given to you, you can take derivative of this integral using this formula, where g of x and t and partial derivative of g with respect to x are continuous functions in the domain D in the xt plane that contains the rectangular region R. The region R is given by this domain. X is between A and B, and T is between T0 and T1. And the limits of integration alpha of x and beta of x are defined functions having continuous derivatives for all x belonging to the interval A and B. We note that Leibniz rule is usually presented in most calculus books because this formula is very important and very useful, and in many applications you need to take derivative of some integrals, so it's very usable formula in many different books of mathematics. We will show in some examples that how you can apply this rule for taking derivative of an integral. For example, in the first example, we want to find the derivative of this expression, actually the integral of x minus t squared u of t dt from 0 to x. So instead of alpha of x, we have 0. Instead of beta of x in general formula, we have x. Instead of the function g of xt, we have x minus t squared ut. So by applying the formula, we have alpha prime of x equals 0, beta prime of x equals 1, and we need to take the partial derivative of g with respect to x, and you know that the function g of xt equals x minus t squared times u of t. So if you take partial derivative of this function with respect to x, you easily have 2 times x minus t to the power 1 times u of t. By replacing all these expressions in the main formula, we obtain the derivative of this integral equals the integral of 2 times x minus t times ut dt from 0 to x, because the first two parts will be equal to 0. One of them because of this, and the second part that here, since alpha prime is 0, we have this part 0. And here, since the function g is given by this formula, we will have x here, and it will be equal to 0. So the first two parts will be 0, and only the last part or integral part will remain. Is it clear? Okay. As the second example, we want to find the derivative of this integral. Once again, you can see that the function g of x and t is given by x minus t times u of t. It is completely clear that alpha of x is 0 and beta of x is x. So alpha prime will be 0 and beta prime will be 1. By replacing all the expressions in the general formula, we obtain the derivative of this expression equals integral of u of t dt from 0 to x. You can see that this expression actually is the one that we have here without considering these two. So by taking 2 times derivative from this expression, we will obtain something like this. Actually, I said you should consider these two also. In the next example, we want to obtain the derivative of the integral that was appeared in the previous example. So, once again, instead of g, you have the function u, and you know that you have the function u of t. You know is x, and the partial derivative of g with respect to x is equal to 0. So by replacing the expressions, you just have the second part here, the first part actually, depending to beta, and the two others part will be 0, so we only have u of x. So the derivative of this integral is equal to u of x. Okay, this formula, I mean Leibniz rule, was introduced in order to help us to transform a Volterra integral equation to an equivalent differential equation. Let's check how we can do this. For example, we want to find the initial value problem equivalent to the Volterra integral equation given in 59. To do this, we take derivative from both sides of this formula. It's completely clear that in the left side, we easily have the derivative of the function u. And in the right side, by taking the derivative with respect to the variable x, here we have 0. And for the second part, by considering the last example here, we will have u of x. So we obtain u prime of x equals u of x. This is the differential equation equivalent to this Volterra integral equation, but we need one initial condition to have the initial value problem equivalent to our Volterra integral equation. For obtaining the initial condition, we just need to put 0 instead of x in our equation. If we set x equals 0 in both sides of this integral equation, in the left side we have u of 0, and in the right side we have 1 plus the integral of u dt from 0 to 0. And you know that the integral from a to a of a function is always equal to 0. So we obtain u of 0 equals 1. And our initial value problem will be the problem that is given in C1. U prime of x minus u of x equals 0 with initial condition u of 0 equals 1. Okay, whenever you have a question, you can ask.
No question, doctor. Thank you.
No question? Okay. No? Let's continue. We have, do you have question?
In general formula,
Okay.
there is a second part of x and derivative. Sorry.
Well, let me
G
bring
of
it.
x, alpha x.
Okay.
Why it's sign of minus?
The sign wise, you have to check the proof of Leibniz rule. It didn't bring it here, but this formula has a proof. You can check. If you want, we can after, because it's a very important formula in calculus. You know, in calculus, two parts are very important, derivative and integral. Okay, in the integral part, one of the most important formulas are the Leibniz rule, and you can see it in many books that are about calculus. The proof is given in many books. You can search in the internet proof of Leibniz rule and you can check the procedure. Okay, let's go to the next example. Once again, we have a Volterra integral equation and we want to obtain its equivalent initial value problem. Here we have the integral equation given in 62, and once again, for obtaining the initial value problem, we take derivative from both sides. In the left side, it simply gives u prime of x, and in the right side, we have derivative of x, which is 1, plus derivative of the integral of t minus x ut dt from 0 to x. And for this case, we had the example 2 in the previous section that gives the integral of ut dt from 0 to x. So we replace it and obtain this actually formula. And this negative sign that you see in the actually behind of the integral is because here you have x minus t, but here you have t minus x. And because of this negative sign, we have negative sign here. Okay? So by taking derivative one time, we obtain u prime of x equals 1 minus integral of ut dt. For obtaining the initial value problem or differential equation, we shouldn't have this integral part. So it's necessary to differentiate once again from both sides of the resulted equation. So we take derivative in the left side. We easily have the second derivative of u with respect to x. And in the right side, for the first term, we have 0. And for the second term, as we obtained before, we have u of x with negative sign that we had. So we obtain the second derivative of x, of u with respect to x, is equal to negative u of x, or the second derivative of u plus u equals 0. Here we have a differential equation of second order So we need two initial conditions. For obtaining the initial conditions, we go back to the main problem. Set x equals 0 in both sides equals 0 plus this integral which gives 0. U of 0 is obtained equals 0. For obtaining u prime of 0, we use equation 63. So we set once again x equals 0. We have u prime of 0 equals 1 minus 0, or u prime of 0 equals 1. And these are two initial conditions which are necessary to have the initial value problem. The next example is also a Volta integral equation, and we are supposed to transform it to an equivalent initial value problem. So we take derivative from both sides with one time differentiating. We have u prime of x equals 3 times x squared plus 2 times the integral. Once again, we take derivative, so we have the second derivative of u equals 2 times 3, or 6x, plus the derivative of this term, which is the integral of u dt. So we have the second derivative of u equals 6x plus 2 times the integral of u dt. And once again, to avoid this integral part, we take derivative from both sides. So we have the third order derivative of u is equal to 6 plus the derivative of the second part or integral part, which gives u of x. So we have 6 plus 2 times u of x. This is the differential equation equivalent to our Volta integral equation, but to have the initial value problem, we need 3 initial conditions, and you know that these 3 initial conditions are obtained using our consecutive equations. From the first one, we obtain u of 0, which is easily equals 0. From the second one, this equation, we obtain u prime of 0, which is once again 0. The next equation gives the second derivative of u of 0, and once again it's equals 0. So our differential equation is given by this way, and our are given by 0. And this is the equivalent initial value problem to the equation given in 67. Okay, now we want to do reverse. Actually, an initial value problem is given, and we are supposed to obtain the equivalent Volta integral equation. To do this, we actually need a formula. In this formula, we can see that how we can take successive integral of a given function. So if a given function f, this function f is given, how we can take or apply integral n times integral to this function. This formula helps us to do this easier. Actually, you see that n times integration of the function f is equal to 1 over n minus 1 factorial times the integral of x minus t to the power n minus 1 f of t dt from 0 to x. So this formula is very important for us to transform an initial value problem to an equivalent Volterra integral equation. For example, if you apply integral 2 times to the function f, it is equal to the integral of x minus t f of t dt from 0 to x. By considering this formula for n equals 3, we have another important relation, that the integral of f is equal to 1 over 2 factorial the integral of x minus t squared of t. You can continue this process for every n. So the main formula that you need to transform an initial value problem to a Volterra integral equation is this formula. For the process of converting Volterra integral equation to initial value problem, you need Leibniz rule, but to do reverse, you need this formula. Okay, here there is a note that says the right hand side of formula 71, this formula, which is double integral of the function f, the right hand side, if you remember, if we set it I of x, by taking derivative of this function using Leibniz rule, we integral of f from 0 to x. And if we take integral from the both sides of this formula, we can easily see that I of x is equal to double integral of f dt. Actually, it is trying to prove the first part here, the first relation using the general formula 71, using the Leibniz rule. So to prove it, we first suppose that this is I of x, and we just need to show that I of x is equal to the left side of this equality. So first it takes the derivative of this relation, and then it takes integral to obtain the left hand side of the formula. Did you understand how it proved this formula? Okay. Actually, this is the proof of this relation. Okay, for the special case when you consider. But it tries to prove this relation. Okay, we have a general formula. For this general formula, for the case n equals 2, gives the relation 71. Yeah, am I right? Is it true? If I consider n equals 2, yeah? But it tries to prove this. If you have this formula, you can easily take another integrals and successively using of this formula gives the general formula. We want to prove this formula, the first one. Suppose that the right hand side equals I of, we don't know I of x, okay? We just set it equal to the integral of x minus t f of t dt. Okay? If I show that I of x equals to this expression, do I show that these two expressions are equal? Yeah? Okay. So I suppose that I of x equals the right hand side. I take derivative from both sides of this relation. I have I prime of x equals, for taking derivative from the right hand side, I use Leibniz rule. So I have the integral of f dt from 0 to x using Leibniz rule. Okay? Once again, I take integral from both sides of this relation. So I have the integral of I prime of x, sorry, minus I of 0. And in the right side, we write down the same expression, double integral of f. So here, I of f equals 0. Why? Because if we set 0 here, we have I of 0 equals the integral of this expression from 0 to 0, which is 0. So we have I of x equals double integral of f, which is the expression in the left hand side of this equality. So we prove that the equality 71 is true. Did you understand? Mr. Muhammad? Clear? Okay. Okay, you're welcome. Okay, now we want to use this formula to convert initial value problems to their equivalent integral equations. before that, we first have some integrals that we want to obtain the equivalent relation using the general formula. Here, it is completely clear that we have 4 times integration of the function u, so we have 1 over 4 minus 1 factorial, 3 factorial, the integral of x minus t to the power 4 minus 1, 3, u dt. And here we have 3 times integral, so n is 3, and this is equivalent to 1 over 3 minus 1 factorial, 1 over 2 factorial, the integral of x minus t to the power 2, which is 3 minus 1, ut dt. Okay, now we have this initial value problem, that the initial conditions are given in 81. So we have a differential equation of order 3. So we need 3 initial conditions which are given by these formulas. And we want to transform this initial value problem to an equivalent Volterra integral equation. We suppose that the third order derivative of y is equal to the function u. We actually set this. We set u of x equals to the third order derivative of y. Now we take integral from both sides of this equality. So we have the second derivative of y of x minus the second derivative of y of 0, which is the integral of the left side here, the integral of this expression, equals to the integral of this expression. So we have here the second derivative of y of x minus the second derivative of y. With the right side, we have easily the integral of u. And from the initial conditions, we have the second order derivative of y of 0 equals gamma. So we can easily replace this expression and obtain the second order derivative of y is equal to gamma, goes to the right side, gamma plus integral of u from 0 to x. Once again, we take integral from both sides of this relation. So in the left side, we have y prime of x minus y prime of 0, and y prime of 0 is given by the initial conditions equal beta. So we have y prime of x minus beta equals the integral of gamma, which will be gamma x, plus integral of u dt dt. And for the second part, that we have 2 times integration, we can use the general formula. And here we have the equivalent equation to equation 84. Once again, we take integral from both sides of this relation, and the left side gives y of x minus y of 0, and the right side gives the integral of beta, the integral of gamma x, and the integral of this double integral. So using the initial conditions that the value of y of 0 is alpha, by replacing this value we obtain y of x equals alpha plus beta x plus gamma x squared over 2 plus triple integral of u. Now here we know that this triple integral is equal to 1 over 2 factorial, or 1 over 2 the integral of x minus t squared ut dt. So finally we obtain the equivalent integral equation as we see here. Y of x equals alpha plus beta x plus 1 over 2 gamma x squared plus 1 over 2 this integral. And for being more clear, we can introduce some notations. For example, we can consider this part as the function f, and also we can consider 1 over 2 times x minus t squared as the kernel k, and rewrite this equation as y of x equals f of x plus the integral of k of x t ut dt. But as you remember, first of all, we suppose that the third order derivative of a y is equal to u of x. So by taking into account this relation, we can write u of x equals f of x plus the integral of k of xt ut dt, where k of xt equals to this expression and the function f is given by this relation. So you have to pay attention that all functions in the equivalent Volterra integral equation should be in terms of the one unknown function, which we considered u of x here. If there is a question, you can ask. No question? Okay. Let's go. Okay. Let's continue. The next example, once again, is an ordinary differential equation with order 3 with 3 initial conditions, and we want to obtain the equivalent ultra integral equation. As the previous example, we suppose that the third order derivative of y equals u of x. We do the same procedure. Actually, if you pay attention, this equation, this is a special case of this general form of equations with a special p, q, r, and g. So we can consider the same procedure with p, q, r, and g given in this special example. You can see that p is -3, and the second actually multiplication is -6. The noun function in the right side is 0, so you can replace in the general formula all related functions and obtain. We have the same procedure. You can see obtain y of x equals 1 plus x plus 1 over 2x squared plus the integral part, and by considering the previous equations, we can write the equivalent ultra integral equation as u of x equals the right hand side of this equation. Please compare this equation with the general one, with the coefficients p, q, r, and also the noun function g, special for this example. In the next example, we have a differential equation of order 2, as you can see here. The second derivative of y plus y equals cosine of x with initial is 1. Using the same procedure, we set the second order derivative of y equals u and take integral from both sides. So let me show you one thing here. As you see in the general case, as you see, we obtained equivalent from here. Let me clear the page. You have the second order derivative, the third order derivative equals u. The second order derivative equals to this expression. The first order derivative equals to this expression, and the function y itself equals to this expression that we can use the general formula of multiple integral for 85 and 86. And finally, we replaced all of them in the main problem, okay? And obtained the equivalent integral equation, this integral equation, by replacing all equivalent expressions. So, using the same procedure here, we suppose that the second order derivative of y equals u, so here we have u. We find equivalent expressions for y of x. So by integrating from both sides of this expression, we have here y prime of x minus y of 0. Y of 0 is 0, so we have y prime of x equals integral of u. Once again, we take integral, so we have y of x minus y of, here we have y prime of 0 equals 1. I made a mistake here, y prime of 0, here we have 1. So let me clear the page and write it once again, y prime of x minus y prime of 0, which is 1, equals the integral of u. And once again, I take the integral, so we have y of x minus y of 0 minus integral of 1, which is x, equals double integral of u. Here, we use the general formula. We have the integral of x minus t u dt. So we replace all equivalent expressions for the second derivative, which is u, the first derivative, which is given by this formula, in the main problem, and obtain the equivalent integral equation. Clear? Is there any question? Okay. Okay, as you mentioned, we have transformed an initial value problem to Volterra integral equation, and also we transformed a Volterra integral equation to initial value problems. What about Fredholm integral equation? If you remember, for Fredholm integral equation, the lower bound and upper bound are considered constants or fixed numbers. We have the integral of some expression from a to b. Here we want to check that boundary value problems means differential equations with boundary conditions. The value of function, for example, is given on boundary. If a is 0 and b is 1, for example. This is just an example. We should have the value of y at 0 and also the value of y at 1. Since we have the value of our functions on boundary, we call this kind of problems boundary value problems. But in to Fredholm integral equation. Here, we see the procedure in an example to understand it better. We have this differential equation, the second derivative of y plus y equals x, and the domain of the actually problem is 0 to pi. The conditions are given by y of 0 equals 1 and y of pi equals pi minus 1. Similar to the procedure we explained for initial value problem, we said the second order derivative of y equals u of x. By taking integral from both sides, we have here y prime of x minus y prime of 0. But pay attention that we don't have this value. So somehow we have to obtain this value and replace the equivalent value in this actually equality. So we have y prime of x equals y prime of 0 plus integral of u. Okay. We have to find y prime of 0 in some way and replace it in our equation. Once again, integrating both sides of this equality gives y of x minus y of 0 equals integral of y prime of 0, which is a constant number, plus integral of u dt. This expression using our general formula is actually equivalent to this integral. So we have y of x equals y of 0, which is 1. So we have y of x equals 1 plus the integral of this expression is x times y prime of 0. We have y of x equals 1 plus x y prime of 0 plus the integral part. Here we need this value, and for obtaining this value, you know that you have the value of y at point pi. So you can use this value to obtain the value of y prime of 0. If we set x equals pi, then we have y of pi equals 1 plus pi times y prime of 0 plus the integral of x minus t ut dt from 0 to pi. So I replace instead of x, pi. We have y of pi equals 1 plus pi y prime of 0 plus the integral of x pi minus t because we have to replace pi instead of x ut dt from 0 to pi. Now we can write y prime of 0 in terms of the other expressions. So if we solve this equation for finding y prime of 0, we have y prime of 0 equals 1 over pi minus 2 minus the integral of pi minus t ut dt from 0 to pi. Now that we have the value of y prime of 0, we go back to our equation 112 and replace, instead of y prime of 0, the expression equivalent to it. So we have y of x equals 1 plus x times y prime of 0, which is this expression, plus the integral of x minus t ut dt from 0 to x. Now, we substitute equation number 109 and 115 and 109 in our main problem. So we get u of x equals, actually we replace all expression present in the main problem in it. Okay, we set actually here instead of the second derivative u, and we obtained an equivalent expression for y. We replace all of them in this equation and obtain u of x equals to the expression in the right hand side. Here we have the integral of a expression from 0 to pi and from 0 to x. We have the identity that the integral of an expression from 0 to pi is equal to the integral of that expression from 0 to x plus from x to pi. So we can use this identity and replace it or use it here. This quality, and obtain u of x equals this expression. After performing some simple calculations and adding integrals with similar limits, we obtain u of x equals the right hand side of this expression, or equivalently we can write u of x equals 2x minus pi over pi minus the integral of k u from 0 to pi, that the kernel k is given using the equation number 119 as this expression. Actually, the function k or kernel is a piecewise function which is defined for the value of t from 0 to x, as we see here, and for the values of t between x and pi, as we see here. Okay. You can check the process, and if you have any question, you can ask.
No question. Thank you, Sarah.
No question. Thank you. Like if you write down, if you write down the process, you can understand it easily. It's very easy. You just need to find the equivalent expressions for all expressions that you have in your equation. For example, if your equation has y prime, the second order derivative, third order derivative, the rule is that always you set the highest order derivative equal to the unknown function u. take integral step by step until you obtain expressions for the first order derivative, the second order derivative, and the function itself instead of, for example, in terms of the function u, and replace all of them in the main equation. This is the procedure. Just some calculation, playing with integrals, and something like this. Is there any question? Okay, I think that's enough for today. We have some examples for section 1.4 and 1.5 and 1.6 also. You can check the exercises. Just to not being worried, you don't need to solve all the problems, okay? Because there are many problems in each section. You just need to solve some problems that are more difficult because some of them are very similar. If you solve one of them, you can easily solve the other ones. You can choose one of them as candidate and solve that one just to be expert in, okay? Just to be expert in solving problems. Okay, if there is no question, we can finish our lecture. No question? You're welcome. Please study well because we need these actually formulas. Today I explained two important formulas. The first one, Leibniz rule, and the second one, which is very important, of course, for the students who wants to work on calculus, on fractional calculus. The second expression that you have, equivalent expression for multiple integral, is very important. In fractional calculus, that formula is generalized, and we actually define integral of any arbitrary order, not, for example, order n, which is an integer number. You can define integral for any arbitrary order. So these two formulas are very important for us. Okay, goodbye everybody. Have a good day.
Goodbye, Doctor. Thank you.
Goodbye.
Goodbye, Doctor. Thank you.
Mr. Ahmad is sleepy. Goodbye, Doctor. Thank you.